Problem sheet 3, question 4. Consider an MM infinity queue with arrival rate lambda equal to 6 and mu is equal to 8. Find the probability that there are no customers in the system, P0, the expected number of customers in the system, lambda, the expected time spent in the system, W, the expected time spent waiting in the queue, WQ, and the expected number of customers in the queue, LQ. So for this we have some formulas, but we also have some intuition. So from the lecture notes we will have seen that P0, the probability that there are no people in the queue, that is equal to e to the minus theta, where theta this time is equal to lambda over mu. Theta is not the traffic intensity because traffic intensity does not make sense for an infinite queue. So this would be e to the minus 6 over 8. We can calculate that as 0.47237. Two of these are quite easy to work out. So we know that WQ, the expected amount of time spent in the queue, well, for an infinite server queue, nobody waits. So WQ must be equal to 0 as nobody waits in an infinite server queue. Similarly, LQ, nobody waits, so the expected number of customers in the queue must be equal to 0. W, which is the expected amount of time spent in the system. Well, as we said before, the expected amount of time spent in the system is equal to the amount of time waiting plus the expected time spent in service. We know nobody waits, so this must be entirely the expected amount of time spent in service, which is going to be 1 over mu, which is going to be 1 over 8. And finally, L, the expected number of customers in the system. Well, from Little's law, we know that that is equal to lambda W. Remember, Little's law works for all work-conserving queues. It doesn't matter how many servers there are. If L is equal to lambda W, these are two things we have. That is equal to 6 times an eighth, which is equal to 3 over 4, 3/4 of a customer in the system on average.